Okay, I wanted to show or talk to you guys about dipoles and molecular polarity today. A dipole is when you have a small distance and then you have opposite charges that are separated. In chemistry, we show a dipole with an arrow, and the arrow is always going to point to the element that has higher electronegativity. And you don't have to necessarily look up the values, just remember fluorine is the most electronegative, so the closer it is to fluorine, the more electronegative it is. This part of the arrow is kind of representing a positive, because these are electrons that are pulled to the element with the higher electronegativity, then that kind of exposes and makes the element with the lower electronegative slightly positive. So we can show this, for example, with hydrogen fluoride, my Lewis structure. And what I would do is I can show the dipole is these electrons right down here that I'm talking about. The fluorine's going to pull harder on those and cause the hydrogen to be slightly positive. So that's the bond, whether it's polar or not polar. We can also have those dipole bonds, or the polar bonds, add up and cause a molecule to be polar. It could possibly accumulate and become polar as a molecule, or it could possibly cancel. So what I mean by that is, this is representing water. I'll just redraw it over here. We don't normally draw it bent, but it's helpful to see it bent just for this. And then you guys know that we would have our two lone pairs of electrons. So because oxygen is more electronegative, we would have a dipole, which is the oxygen pulling harder on the electrons that are in the bond. Same thing here. So because of the dipole arrows and the lone pair electrons that are going to be there, this molecule is polar. So that means that this molecule is negative on one end and positive on the other. So in class we did a PHET to kind of play around with this and to try to see how the shape of a molecule relates to its molecular polarity. So I'm going to show you some examples and then we'll make some rules. So this PHET is on Schoology, so you can definitely play with it. So for example, up here I have nitrogen, diatomic nitrogen, so just a nitrogen bond into a nitrogen. So because they're identical elements, they're going to be pulling on those electrons exactly equally. So if I click on this electrostatic potential, I don't see any red or blue because everyone's sharing those electrons perfectly equally. So this is an example of a nonpolar molecule. Here's the hydrogen fluoride. So the gray arrow is representing the bond dipole between the hydrogen and the fluorine. The fluorine's going to be pulling on the electrons. And then the yellow arrow is representing the molecule polarity. So there's a negative buildup on the side that has the fluorine. And I like this view. You can still see, if you see the gold arrow, we know that it is polar. But the red accumulates and shows us that there's more negative on that end, and the blue, there's more positive or less electrons on that end. So now I want to kind of look for themes. So what we're going to do is look at shapes. So one thing that I do to explain this is I think about dogs playing in a dog park. Sounds silly, but my dogs are playing with, some kind of a toy, and they're pulling on the toy. The toy would be the electrons. And you have to think about, will they pull equally and essentially go nowhere, or will one pull harder than the other? So if I go back to my PHET, and let's say I'm talking about methane. And methane is natural gas. It's what we burn in our houses for heat in the winter. It's what a lot of our dryers and stoves run on this. So, but what I'm trying to show you, if we go back to the dog park analogy, would be the white hydrogens would represent like a small dog, like let's say a Chihuahua. So there's 4 of them pulling, so the electrons really, or the dog toy, if you think of it, it's not going to go anywhere. I can click on, you know, my electrostatic potential, and I don't really see any bright reds or blues. So I can kind of see that these hydrogens, the gray is representing the bonds. The bonds are polar between the carbon and the hydrogen. Carbon pulls on those electrons more. But overall, it's going to be a cancellation. So this molecule, you don't see the yellow arrow. It's non-polar. So this is a tetrahedral shape. Let's look at another tetrahedral. So let's say we have, now again, thinking of the dog thing one more time. The white would be like the little dogs, and then all of a sudden I put in a really big, like a Great Dane. So this is highly electronegative, and it wouldn't have to be this huge electronegative, but it's a different. So unless they're all identical going around the central atom, which would be the carbon, for a tetrahedral shape, the overall the molecule is going to be polar. So you see the yellow gold arrow. We can show it this way. There's a darker red up on one end, which means that end of the molecule is negative, and the blue end is positive. We can also look at trig planar. Trig planars are, again, like the tetrahedron. As long as the element around the central atom is the same, then they're the dipoles that are for the bonds, they're going to cancel out. So there's no lone pairs on this middle atom, so that's why we know this is always going to be a nonpolar molecule for trig planars as long as the element going around is the same. So when are we always going to be polar? We're always going to be polar when we have a bent shape. And bent shapes, you have to realize, they're on the top of that oxygen for water. Remember, there's those 2 lone pairs of electrons. That alone makes it negative on this end. So bent shapes are always polar molecules. And then also trig pyramidal shapes are always polar. Because again, remember, there's a lone pair sitting up here. That's negative. So that's going to cause that end of the molecule to become slightly negative, and then the opposite end gets slightly positive. Linear, some of the linear shapes like carbon dioxide, these ones I usually just think through. So here the oxygen pulls, the gray arrow is pulling on those electrons away from the carbon, and so is this oxygen. But overall, it's like a tug-of-war, and this is a cancellation of those dipoles. And you can see that we don't have the bright reds. It also shows here we don't really have the really dark and light gray. And we don't see that gold arrow here. So this is a nonpolar linear molecule. But it's also possible to have linear molecules where the central atom and then what's going around it, the nitrogen and the hydrogen, aren't the same. So they are not able to cancel out. So in this case, the dipole, the gold dipole of the whole molecule is going to be in the direction of the nitrogen. So if you have a linear shape with 3 atoms in a row, if the 2 on the outside are not the same, then it'll be polar. And again, you can see this clearer when you click on some of these different views. So in summary, we can probably, kind of summarize this by saying that which shapes are always polar? We would say bent and trig pyramidal because they have lone pairs. Nonpolar, we don't have an always, but for tetrahedron and for trig planar, both of these shapes, they will be nonpolar if the atoms bonded to the central atom, the one in the middle, are the same. So if they're not all the same, then it's automatically polar. And then the other shape that we did not cover is linear. We talked about it. I don't really have a rule. When I think about linear, I just say think. And you're going to think, the question you're going to ask is, will the bond dipoles cancel? So if you have hydrogen with chlorine, you're not going to be able to cancel that. But if you have carbon dioxide, the pull that goes this way for this bond and this way for this bond, that's going to cancel out. So there's not going to be a polar molecule that results. And then another example, here the atoms around the central atom are not the same, so they will not be able to cancel, so this would be polar. So this one will end up being a polar linear, a non-polar molecule of linear, and a polar linear. I hope that helped.